Good morning class. Today we are going to study about the next oxidizing agent, that is PCC. Full form is Pyridinium chlorochromate. There is an alternate name for this reagent, that is Corey-Suggs reagent. So this is the structure of Pyridinium chlorochromate. This is chlorochromate and this is pyridinium ion. It's a milder version of chromic acid. This is the structure of chromic acid, H2CrO4. So it's slightly milder oxidizing agent as compared to chromic acid. If we look at the preparation of PCC, when chromic trioxide is dissolved in 6 molar HCl solution, chlorochromic acid is obtained. And on treating chlorochromic acid with pyridinium chlorochromate reagent is obtained. This is not a particularly hygroscopic reagent, so it's stable and it is very easily available commercially and can be stored. The solubility is mainly in organic solvents, especially dichloromethane. Most of the reaction you will see will be in dichloromethane only. And reactions take place mostly in room temperature. DMF, on the other hand, promotes the over-oxidation. When we use PCC for oxidation of primary alcohol, it converts primary alcohol to aldehyde in dichloromethane. But if DMF is present, then alcohol gets oxidized to carboxylic acid. So depending upon what product is required, whether we need to oxidize primary alcohol to aldehyde or we need to convert it into carboxylic acid, we will be choosing our solvent. Now moving on to reactions, it is mainly used to oxidize primary and secondary alcohols to aldehydes and ketones respectively. Now it is more selective as compared to the Jones reagent. Jones reagent is chromium trioxide in presence of sulfuric acid. The conversion of primary alcohol to aldehyde is only possible if there is no water content present in the reaction mixture. If our solvent contains some amount of water, the oxidation will proceed till carboxylic acid. So, and if there is no water present, the oxidation will stop at aldehydes and it will not go up to carboxylic acids. Let's look at the reactions. Here we have heptanol. When treated with pyridinium chlorochromate in presence of dichloromethane, it gets converted to aldehyde. It's a primary alcohol getting converted to aldehyde, heptanol. Second is a secondary alcohol. Again, when we treat it with PCC and dichloromethane, acetophenone is forming. That is a ketone. Now, again similar reaction is there. It's a primary alcohol treated with PCC in dichloromethane. Aldehyde is obtained and chloride salt of pyridinium is obtained. So if we look at the mechanism, how the reaction proceeds, this particular reaction is explained with the help of mechanism. So this is our PCC. The the alcoholic oxygen attacks the chromium and this oxygen takes up this bonding electron and gets negatively charged. So this kind of adduct is being formed here. Our oxygen is getting negatively charged. This proton will be lost and one of the negatively charged oxygen will take up a proton. This will be lost to the solvent and this oxygen will take up a proton from the solvent. Now, moving further, there is again the double bond formation of oxygen with chromium, and chlorine will be our leaving group in the form of chloride. Cl negative will be removed. So this Cl negative will be present in the form of ion in the solvent only. Moving on to, we have this substance with us. Chloride ion will attack one of these protons. These protons, or you can say the CH bond, is activated due to the presence of oxygen. So this chloride will attack the proton, take up it, and this bonding pair electron will go to oxygen to form a double bond. This bond will be cleaved and we will obtain our benzaldehyde. So this benzaldehyde is obtained, and other substances, chromium, one double bond oxygen will remain as it is, and 2 hydroxy group, this OH, this will become O negative. It will take up one of the so this is OH and this is O negative. So it will take a proton from the solvent and form this. So this is how the reaction proceeds for PCC. Moving on to the next reagent, Pyridinium Dichromate. So if it is known as Cornforth reagent. If we look at our PCC and PDC, there is very slight difference, and that is PDC is actually a kind of dimer of PCC. In slight some ways we can say that. Okay, so now this is a stronger oxidizing agent, but it only converts primary alcohol to aldehyde and secondary alcohol to ketone only, similarly as that of the PCC. But this PDC is rarely used because it is associated with toxicity. So this reagent is rarely used. Now melting point is 152 to 153 degrees Celsius, soluble in DMF, DMSO, acetonitrile, sparingly soluble in dichloromethane, chloroform, acetone, and completely insoluble in hexane, ether, ethyl acetate. It's a bright orange solid and it is widely available. For handling and storage, it can be easily stored in the dry form, even in contact with the air. Reaction solvent must be anhydrous and free of reducing impurities. Same as that of the PCC. PCC was sensitive to water and it was converting primary alcohol to your carboxylic acid. So same goes for PDC. In this also your solvent should be anhydrous and free of the impurities. It's now the toxicity of PDC is suspected to be a cancer agent. So it should be used only in the fume hood. And if we talk about the property of PDC, it is less acidic as compared to PCC. So therefore it is more suitable for the oxidation of acid sensitive substrates, those substrates which decompose or which give some reactions in the acidic atmosphere. In those cases it can be used. Preparation. Now PDC is also prepared from chromium trioxide. Chromium trioxide is first converted to chromic acid on treating it with water, and chromic acid on dehydration becomes dichromic acid. Basically it is getting dimerized with a condensation reaction. Water molecule is being condensed and you are getting dichromic acid. Now to this dichromic acid, pyridine is added to obtain pyridinium dichromate. If we look at the reactions are very similar. So this is a primary alcohol. So obviously we will obtain the aldehyde. So this will be our product. Here we have a secondary alcohol in presence of PDCC. On reaction with PDC in presence of dichloromethane, will obtain a ketone. Again a primary alcohol. So what you will obtain? Aldehyde. Another reaction, secondary alcohol. It doesn't matter what that we have a tertiary butyl group on the para position. We again obtained a ketone. Now moving on to this, PDCC will not affect the double bond or this oxygen. Only this will be getting oxidized. So the product here is aldehyde again. Now the next oxidizing agent that we have to study is DTBP. DTBP is 1,1-di-tertiary peroxide. Another name could be tertiary butyl peroxide simply. If we write the elaborated structure, so it is this. This peroxide bond, in whatever compound it is present, it is very weak. It breaks up very easily. Homolytic cleavage of this bond takes place and two tertiary butoxy radicals are obtained. These two radicals are obtained. So it's a radical initiator. It initiates anti-Marconics of addition of HX to alkenes. Now what could be the X? X could be halogens, sulfur, silicon or phosphorus. It is soluble in organic solvents. So we can perform reactions in the solvent which are organic, and we can perform these reactions only on the compounds which are soluble in the organic solvents only. If we talk about the precautions in handling and storage, so it's a radical initiator, so it should not be inhaled or it should not be brought in contact with your skin. It's a strong oxidizer. It's easily flammable, so we have to store it away from the heat. Always keep it away from the heat, otherwise there will be a explosion. Now, di-tertiary-butyl peroxide is commonly used as an initiator for radical reactions. We have already talked about the unimolecular decomposition to obtain two tertiary butoxy radicals. These radicals further break down into your acetone and methyl radical, and this methyl radical further take up the reaction, like it will take part in the initiation and propagating steps of the reaction. Half-life of DTBP is approximately 3 hours at 140 degrees Celsius and 24 hours at 120 degrees Celsius. So according to the requirement of our reaction, at what pace we want to proceed the reaction, the oxidizing reagent can be used for those reactions which proceed at a temperature range of 110 to 150, because only during this range we will be getting steady concentration of our radical, initiating radical, that is these initiating radical will be available for this much time at 140 degrees Celsius and 24 hours for at 120 degrees Celsius. So depending upon our requirement, if the reaction proceeds aggressively, then we will be taking it at a lower temperature, so that the aggression of reaction decreases, and it might take longer time, but there will be no explosion. So depending upon what our requirement is, we'll set up the reaction temperature and will proceed with the reaction. Now, alkoxy radical are electrophilic and they initiate the reaction by abstraction of CH bond, like the CH bond which are attached to heteroatom. Heteroatom could be your oxygen, nitrogen, sulfur, so that ways. And the resultant radical undergo a variety of CC bond formation reaction, including polymerization. So you will understand this better when you will be looking at the reactions and the mechanism. First of all, if we look at the mechanism, it's a reaction initiator. So our DTBP, that is 1,1-di-tertiary-butyl peroxide, will undergo homolytic cleavage and 2 tertiary butoxy radicals are formed. These could undergo further cleavage to form methyl radical and acetone. So this as well as this, any of these two could act as an initiator for our free radical reaction. So if we have a compound with CH bond, the initiator will abstract one of the hydrogen and it itself will get in a stabilized form but convert the compound into the radical. Now this is one of the reactant. It gets converted into radical. Now if we look at the propagation step, this radical will react with another reagent, another reactant, and undergo addition reaction. Bond formation will, this is electron rich double bond. So it will attack the radical. The pi bond will cleave. One of the electron will combine with this radical electron and form a bond. So this bond is formed, and this one of the electron will come on this carbon and form a radical here. So this is what is happening. Now further more additions can take place. Again, next reactant molecule will come and combine with it. There are other possibilities. This, depending upon what are the XY groups are here, this could get rearranged, fragmented, and undergo different kind of radical reactions. It's just a simple general mechanism that is shown here. Now chain transfer. Now this molecule is formed. It will again react with our first reagent present in the solution, and it will get stabilized, while the second compound gets converted into radical. This will again be consumed in the propagation step. So that ways your chain propagation will keep on going. Now if we talk about the termination step, two of the radical can dimerize and form a stable species, and there are other radical reactions possible which could terminate this mechanism. Now earlier we studied that the reaction proceeds via abstraction of hydrogen from a CH bond. Now this is favored in case of ethers and amines, or if some heteroatom is present adjacent to that site, because let's see the example of tetrahydrofuran. So in case of tetrahydrofuran, a radical will form on this carbon. Now this oxygen have two lone pair. There is a possibility of slight resonance here. This could form a double bond, or you can say radical shift could occur, not this double bond, single bond only. This carbon will have its complete octet, but this oxygen will be lacking one electron. So the oxyradical formation can take place. Due to this distribution of electron cloud, this species gets stabilized. Similar cases, if we look at the ethers, or we look at the amines or esters, so that is possible in those cases, and that's why the our abstraction of hydrogen is possible by electrophilic oxyradical. Now if we look at the reaction, this is tetrahydrofuran. This kind of radical formation will take place, and if we combine it with this compound in presence of DTBP, 90% yield is obtained and addition product is obtained. Now if we talk about this, again this is carbon with two hydrogens. These hydrogens are activated. This CH bond is an activated CH bond. Again DTBP will facilitate the abstraction of hydrogen, and it will easily undergo addition reaction with our reagent. So this is all we have to study on DTBP. The last oxidizing agent that we have to study is Dibenzoyl peroxide, DBP. Dibenzoyl peroxide also contain a peroxy group. So the mechanism is similar. Cleavage of this bond is possible. In homolytic cleavage takes place, two radicals are obtained, similar to our previous peroxide. If we look at the properties, it's a white crystalline powder with a melting point ranging from 103 to 106 degrees Celsius, sparingly soluble in water or alcohol, but it is soluble in benzene, chloroform and ether. If we remember the previous DTBP oxidizing agent, it was not very soluble in the solvent. So depending upon what solvent we are using, what reactant we are using, will decide which reagent to use. Okay, so coming back to our dibenzoyl peroxide, it is soluble in benzene, chloroform and ether. So we can easily proceed with these three solvents. Again, it is a initiator for radical reaction. Of course, it provides us radical. Half-life of the DBP is 1 hour at 95 degrees Celsius. So if we have some reactants that are stable around 95 degrees Celsius, we could proceed with this oxidizing agent. This homolysis may also be affected by light as well as transition metal catalysis. Now, other than heat, the cleavage of dibenzoyl peroxide to give two radicals is also possible in presence of light or any transition metal catalysts. If we talk about handling, storage and precaution, it's explosive. All peroxy oxidizing agent, you will find that they are explosive. Again, it is harmful if inhaled or if it is brought into contact with skin. Strong oxidizer, susceptible to explosion by shock, friction or heat. It could catch fire automatically at a temperature of around 79 degrees Celsius. All of the experiment involving DBP or any other peroxy compound should be carried out in the safety shield. And before working up the reaction, excess peroxide should be destroyed. For example, if we performed some reaction and we used peroxide, we obtained some compound, and now we want to further react that compound. We want to perform some other reaction on that compound. So first we have to make sure that all the radical species are removed from that compound. None of them is present as an impurity. Otherwise our reaction could get explosive. So before working up the reaction, we have to make sure that all the peroxides are destroyed. Now we have a reagent. We reacted with N-bromosuccinamide, NBS, in presence of our radical initiator DBP in chloroform, and we perform reflux. 65% yield is obtained and brominated product is obtained. We know that bromination generally occur via free radical mechanism. The role of DBP here is to provide the initiator for the initiation of reaction. If we look at the mechanism is of similar way. You have one reactant. Your initiator from DBP will abstract the hydrogen and it will go under it will undergo different possible reactions. There could be addition reaction or rearrangement, or it could further fragment into other species. Now the initiator will react with our alkene and form a addition adduct that further polymerizes, like we have seen in the previous reaction. So in this way it could undergo polymerization reactions. Okay, if we have some XY compound which have an activated CH bond, so what it can do, it can take up one of the one part of that compound and the other will form a radical. That radical species could undergo addition reaction with our alkene, and again it could take up the X part of the your XY compound and Y radical is formed. So this Y radical can again be consumed in this kind of steps. So what is happening? This is a propagation step. Again and again you are generating your Y radical. Y radical was generated here also and here also. So if we once again look at the reaction, what is happening? This is our initiation step. The initiator from our peroxide will abstract the hydrogen, form some one form of the initiator, just like we have seen in the previous reaction. There also the radical, let me show you again. So here also what was happening, we had a initiator, it was cleaving into radical, again further fragmentation was taking place. So if this is the general mechanism for all kind of peroxides, we have a reactant, the peroxide radical will abstract the hydrogen, activated hydrogen, and a radical formation takes place. It could further undergo addition or rearrangement or any other fragmentation reaction. If we look at the propagation step, our initiator combines with the alkene to form a addition radical. This radical have two possibilities. It could undergo further polymerization reaction, reacting with more alkene molecules, or it could react with the one more reagent, XY reagent, and cleaves this XY, takes up the X part and forms a Y radical. That Y radical further reacts with your alkene and forms a addition radical, which again cleaves XY to take up X and to generate Y radical, and this 1:1 adduct of your alkene and XY compound are obtained. So again, if we keep on repeating this step, reacting this Y radical with alkene molecule and then again reacting that radical with XY, these steps could be repeated a number of times and we are obtaining 1:1 adduct of alkene and XY. So that way also this reaction can proceed. And as seen in the previous oxidizer, the termination step could be number of steps, like your Y radical plus Y radical will form YY, or this radical itself react with another molecule of this radical and form a neutral molecule. So that way number of terminating steps could be there. If we look at the reaction, we have alkene and we have HBr and our peroxide DBP. So one is we are getting 1:1 adduct. Okay, two possibilities are there, that hydrogen gets attached here and bromine gets attached here. Another possibility is your bromine gets attached here and your hydrogen gets attached here. But the majority product is this one, and this will be a minor product. So basically DBP is facilitating the bromination of this alkene. It is just acting as a initiator, radical initiator for this reaction.